Cool. Thank you for everyone for coming today. We're just screen recording for the people who can't come today. Today's Qsium session 4. Today we're going to talk about gate-based quantum computing and entanglement. So today we're going to learn about the building blocks of quantum computing, which are quantum gates. Just like logic gates are kind of the foundations of classical computing, quantum gates are the foundations of our quantum computers. Also, if you have any questions throughout the lecture as well, just leave it in the chat, and hopefully someone will answer it for you. So today we'll also going to be talking about entanglement. So if you look at the table of contents, we're going to go through entanglement, quantum circuits, single qubit systems, measuring in different bases, and multiple qubit gates. So last time we learned a bit about something called tensor products or Kronecker products as in the lecture notes. Now, we have to start thinking, what happens if we have 2 qubit systems? What happens if we have 3 qubit systems? How do we represent it algebraically? How do we represent it mathematically? Way to do it is basically by using a tensor product. So if we see on the lecture right here, psi in this situation represents a linear combination of all the kind of 2 qubit systems that's possible. So we have state ket 00. So in that instance, that's when we have that's basically when we have state 0 with another state 0, just like what we were seeing last time as well. And this is what happens when we start looking at multiple qubits as well. And this is also very relevant for entanglement. So let's have a better look at how it actually represents entanglement. So if we look at the state above, which is one of the Bell states, as we will learn more about in the breakout rooms, this is a superposition of the 00 tensor product state and the ket 11 tensor product state. And as you remember, the 1/√2 is necessary because if you want to find the probability of something, you do the modulus squared of something, you do the modulus squared of something. And if you want that, you want the whole state to basically always equals 1. So in the superposition, you want 1/√2 because you have half plus a half. So this is how you can represent tensor products, represent quantum entanglement through tensor products. And we'll learn more about that in the breakout rooms. And we even learn about, we'll even have exercise on how to actually create Bell pairs as well in our breakout rooms. So now, what does quantum entanglement mean? So I know you probably have heard the word entanglement before. You might have heard spooky action at distance, that it has all sorts of kind of philosophical kind of controversy around the subject. And it has had a lot of controversy as well. So quantum entanglement is where 2 or more quantum states are indefinite until measurement. However, they have conditional relations between each other. Now, in the case of in our 5+ state, if we look just back here, we call the 2 states involved entangled because if person A measures one state, we know person B will measure the exact same state. So what we mean by that is if you have, so the difference between kind of like a entangled state and a not entangled state is basically if we have something, let's say this is, let's say we have 2 states, for example. We have ket psi, and let's say we have ket phi like that. If we just have that, that is not entangled. That is in fact something what we say is separable state. And that's because all this is just one simple quantum state. But let's say if we start putting these 2 kind of qubit systems into a superposition where we have like a tensor product like that, plus another kind of something with a tensor product of something, that's what we kind of recognize as to be entangled. And in fact, we actually say our Bell pairs are maximally entangled, and we'll go more into that in the breakout rooms as well. So how do we calculate probabilities? I'll let you actually first read through the slide, and I'll give you like 10 seconds just to have a brief look at what it actually says. So this is looking back at our kind of Bell state, 1 over root 2, but instead of 0, 0, we have 0, 1 plus 1, 0. So let's consider the probabilities for the measured outcomes if we use 0, 1 measurement basis. So if you go back to a few lectures back, we talk about measuring measurement basis. In here, we're just measuring from the computational basis. We say the computational basis when we're measuring using ket 0 and ket 1. If you did some of the problem sets, you might have encountered kind of bracket notation having the plus inside that. That's called the diagonal basis, but in here we are using kind of the computational measurement basis. So let's say, so if we look at the probability of measuring 0, 1, be P1. So if we let the probability of measuring ket 0, 1 be P1, by the Born rule, if we just kind of measure the state ket 0, 0, 1 and put it and try to measure it with the state with the Bell state, if we recall the Born rule that we used in the last lecture, you can see that it simplifies nicely to 50%. Now, for example, the reason why 1, 0 and 0, 1 equate to 0 is because they are orthogonal states. So 0 and 1 are orthogonal. This is kind of what you see in dot products as well. If what we learn in A level, where you have two kind of vectors which are in 90 degrees, but if you do a dot product of them, they will become the answer is 0. And that's basically the same thing that happens. That's basically the same thing that happens with our quantum states, because as we've said before, we're all working in matrices, we're all working in a vector space that follows very similar rules that we are kind of familiar to. So now, if you go back, we have relied on the fact that the inner product is distributive. Now, what do we mean by distributive? So distributive in kind of like a very basic sense is just if you have if you have A, B plus C, this is just AB plus AC. So our tensor products also, so our inner products actually follow that distributive property as well. And that's what we use for when we actually calculate probabilities. Now, in the second, as it says, in the second step, we rely on the fact that to find the dot product between two tensor product states, we find the inner product between each corresponding state and multiply them. On to the next slide. So talked about logic gates and how that is the building block for classical computing. Now, as you'll see, we have quantum analogous kind of gates where we're now working with quantum states instead of classical bits. Before I go on to quantum gates, let's have a look at what what a quantum circuit actually looks like. So we generally represent quantum circuits to have, let's say, for example, 2 qubits. So let's say they have Q0 and Q1. We say they have, we say they're connected to some kind of wire, for example. And we basically also have a classical channel as well that calls C0. And basically, you can use, we can start adding bases, we can start adding gates into it, and start doing interesting stuff with it. And also when we measure it, we go back to our classical channel to actually get our measurement result as well. So if that, that's not the best of diagrams, to be honest, but hopefully that gives you a general idea of how we're actually measuring stuff, is that we both have a quantum kind of quantum circuit with the classical channel as well. Now, what would be the NOT operation? So in classical computing, we call a logical NOT operation to turn one operation that turns 1 to 0 and 0 to 1. So what is kind of the quantum analogous quantum gate that turns maybe ket 1 to ket 1, ket 0 to ket 1, and vice versa? Turns out it's something called what we call the Pauli X gate, or just the X gate, and we use matrices to actually find what these gates are. So this is the Pauli X gate. So what would be the effect of applying this gate on a qubit, ket psi, and this just the general kind of qubit expression for a qubit as well. Turns out if you apply this matrix 0, 1, 1, 0, you actually get the amplitudes. So kind of alpha and beta. So alpha is the amplitude for ket0, and beta is the amplitude for ket1. So it turns out the amplitudes get gets swapped basically using the X gate, which is equivalent to basically which is the equivalent to the kind of classical NOT gate in a quantum sense. Now, this can be thought of rotating by pi radians around the x-axis as well, hence why it's also called the X gate. So if you recall the block sphere that we did in last session, you might remember the kind of how we kind of drew the X, Y, and Z axes for the block sphere. So the X gate does a rotation of pi radians, so 180 degrees around the x-axis. Okay, so so the Y and Z gates perform rotations by pi radians around the Y and Z axes respectively. Yeah, so these are kind of just like other gates that we use in quantum computing. Actually, if you guys haven't, please take note of the X gate. It's used a lot, so it'll be very useful. Yeah, so just take note of the matrix form of the X gate because they'll be useful for you in the breakout room. One thing to notice as well is that in all of our quantum kind of gates, so if a qubits like Q0 and Q1, for example, we always the kind of convention is to always have Q0 and Q1 to start off with ket 0. Now that's just purely convention. It could have been ket 1, but we use ket 0. But if we start putting, let's say, an X gate here and an X gate here, we would just have 1, 1, and that's what we will use in the breakout rooms to make to start off with state 1 as well. But kind of the general kind of convention is that all qubits start off with ket 0. Now, this is probably one of the most important quantum gates, so please make note of this. It's called the Hadamard gate. Now, this gate allows us to create superpositions. So basically, it transforms our ket 0 and ket 1 are kind of transforms a gate. So this is the matrix form, but basically after we apply our Hadamard gate to maybe, let's say, ket 0, we'll basically have ket 1 over root 2. So we're basically having a superposition of states, and this is why the Hadamard gate is really useful. We actually use the Hadamard gate to create a Bell pair, and we'll have a look at that in our breakout rooms. But hopefully this gives you a good idea of why it's useful, because once you start having superpositions, this basically allows us to take advantage of quantum mechanics, and it also shows basically the power of quantum computation as well. And the idea of creating superpositions, as you will see, is very powerful for quantum computing. But this is the Hadamard gate, and yeah, please make note of this, because this will be very useful in the breakout rooms. To move on, this is known as the phase gate. So the P gate performs a rotation phi around the z-axis. So we're throwing a lot of gates at you, really. Not a lot of the gates are commonly used, but we're introducing a lot of gates so that you guys can start kind of having a look and kind of playing around with them. And I'll send you, if maybe Zahir can send you a link in the meeting chat or in Discord, to a link to the IBM quantum experience. You can kind of start use their kind of quantum circuit composer, where you start basically you can put your own gates and see your measurement results as well. So you can actually start playing around with gates. So if you kind of want your own experiment, kind of want to have a play around, look more detail into what kind of circuit composers do, what kind of these different quantum gates do. Yeah, please have a look at the IBM quantum experience as well. These are just more gates. Now the identity gate does nothing to qubit; it's rotates 0 radians. We also use it. You know, in normal kind of A level as well. But the identity matrix, although you might see, well, what's the point of the identity matrix if we're just keeping it the same. But we actually use the identity matrix to make sure that we're measuring. And I forgot. I'll come back to you, but I'll actually put some examples in the problem set as well. But there are useful examples of the identity matrix. And these are just additional gates that might be interesting. So also when we say phi equals pi over 2, if you go back to our thinking about the block sphere representation of our qubit, that's basically we're working in spherical coordinates. So and last week I did tell you this is why the block sphere is really useful representation, because it allows us to start looking at rotations really nicely, looking at what do these gates do to a quantum state. So yeah, so hopefully that kind of answers a lot of your questions on why do we use the block sphere representation for a qubit. Now these are more interesting gates. They are C0 and CC0 gates. So we are now looking at multiple qubits basically. So I'll draw a C0 gate for you. So C0 gate looks like this. Oh wait. C0 gate actually looks like this. Oh yeah, going through a quantum gate. And basically what it does is if we call this qubit the input, and we actually call that not the input, doesn't really matter, but we actually call that the control qubit, and we call this the target qubit. I'm just telling you because if you do any further reading, it's quite useful to know this kind of vocabulary. So C0 and CC0 gate. So what C0 does is if the control qubit is state 0, it does nothing to the target qubit. But if it's state 1, for example, it flips the target qubit. So if it was kept 0 state before, it becomes 1. If the control qubit was was kept 1. Now the CC0 now looks at 3 qubits where we have 2 control qubits and 1 target qubit. But basically what we do is if we have two control qubits which are state 1, then the target qubit basically then kind of inverts our kind of qubit state. So it's very similar, but simply CC0 gate looks at 3 qubit systems. And C0 and CC0 gates are used so much in quantum computing, and you'll have a look again in the breakout rooms. Yes, but they're very useful in quantum computation. So we had a bit of look at multiple qubit systems and how multiple qubits are represented. For example, if you have kept 0, if you have, let's say, n qubits, the kind of input, the starting qubit will be 0, 0, 0, and then it'll all go until 0n. If you have 0, 1, 2, 3, and we basically start thinking of quantum states as multiple quantum states, and also when we look at entanglement, we think of it as a kind of tensor product of all the qubits. So it may not also be clear how an X gate would act on a qubit in a multi-qubit vector, but hopefully we have included all kind of different examples in the breakout room, so hopefully it gives you a better idea of how it all works. Yep, so managing multiple qubit systems. So if you look at the lecture slides, just as we use the Kronecker product to calculate multi-qubit state vectors, we use the tensor product to calculate matrices that act on these state vectors. So that's a lot of kind of mathematical jargon again, but hopefully it'll be much clearer once we kind of work through different examples as well. Because what I feel from my experience is quantum computing comes much more naturally if you start working through different examples. So if you're still kind of slightly confused on how everything works, just kind of sit tight, kind of try to understand it, but it's not a big deal. I mean, it's more crucial that you start to look at kind of different quantum circuits and trying to work out how it all works. And become much clearer how they all fit together. So representing complex amplitudes. So we saw that a single bit has two possible states and a qubit state has two complex amplitudes. Similarly, two bits have four possible states, so 2 to the n. And to describe the state of two qubits require four complex amplitudes, as we see below. So this is a bit about measuring in different bases. So we kind of had a brief look at it before, but if you kind of have another look again about how we actually measure in different bases and what we start to do, and if we want to measure state ket 0, 0, how does that all work? Turns out we follow a very similar rule, just like we did for a single qubit, and the same implications hold, such as a normalization condition, as we see that probability must sum to 1. So yeah, and this is just a short recap on the Kronecker product. If you've kind of forgotten, it's not the easiest thing in the world, but you can just see that what happens when we have tensor products, and hopefully that reminds you of last week's lecture. Yep, so and following the same rules, we can use the Kronecker product to describe the collective state of any number of qubits. Here's an example with 3 qubits. Yeah, so this is you can so basically if you have BA, you'd simply just multiply C as well, and as we've seen last time, this just leads to basically where we have 8 kind of complex amplitudes for a 3 qubit system. Yeah, so that's all said in the kind of quantum notes as well. So one challenge as well is, how do we start controlling n qubit systems? Theoretically, it's all possible, but turns out once you start having 100 qubits, 200 qubits, not only is it a challenge for classical computers to simulate that, it's also a challenge for hardware as well. We'll look at more into hardware in the future, but the problem is that the problem with it is that once you start having a lot of qubits, it causes something called quantum decoherence, basically where kind of different qubits start to entangle with each other, which makes a big mess in our quantum calculations. So it's very much a kind of algorithmic problem, like a computing power problem, as it is in a real life problem as well, where it's starting to get difficult as we start having much more qubits. And this is why there's a big problem in quantum computing about scalability, and researchers all over the world are working on trying to make that into a reality. So we'll look more into kind of like now the SES part of it, now about climate change. That's a great quote from Richard Feynman. I'm sure you guys all know him and all, but he says that nature is in classical damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. Now, Richard Feynman was also one of the first people to come up with the idea of a quantum machine in the 1980s. And he basically started realizing that if you want to kind of simulate much more kind of complex kind of molecular processes, you're going to need different kind of a more quantum mechanical picture of computers. And turns out today what we're starting to do now in the real world is where we're starting to measure much more, trying to simulate different kind of molecular dynamics using quantum computing, and enhanced kind of algorithms such as like quantum Monte Carlo allows us to kind of simulate like thousands of atoms, and as IBM kind of introduces 433 qubit processors, we can expect for that computing power to increase as well. So yeah, so in the here's included a great kind of example that hydrogen fuel cells, although as only 70–80% efficient, quantum computing can actually help and simulate and optimize this process through better research. They actually do it through quantum algorithms, which is actually a topic in 2 sessions. So more exciting stuff ahead. So this is a motivating example. So this is another example about fertilizers, about why quantum simulation, why quantum algorithms is direly needed for applications like climate change, because a lot of it has to do with quantum chemistry and quantum chemistry simulation, because climate change relies a lot about big climate set data. And also in this case, if we want to find a catalyst, a perfect chemical catalyst, which can a perfect quantum, perfect biological catalyst, we want to start, we need to start trying different molecules. We need to start simulating different stuff. And once you start having more atoms, that makes kind of computation much more difficult. And once you start having hundreds of more qubits, that makes computation about 1,000 times faster. So quantum computers can help us find other sources to produce nitrogen and reduce CO2 emissions. So if you are joining the STS curriculum today with Laura, you'll talk more about you'll talk and have a debate about about different solutions to climate change, and to what extent can we actually solve climate change through quantum computation as well. So this is all for the lecture notes, lecture slides. Hopefully everything goes well in the breakout rooms. Do let Danny know if you have any problems or you haven't been assigned to a breakout room, but hopefully you all have. Next week we have a guest lecturer from Qsium, Catherine Spendier, who will actually start thinking about how we can actually ourselves code quantum gates using Python, and they'll introduce a Qsium package called TCARE. So that will be an extremely interesting lecture, and it will put all the knowledge you've learned today to a test. So I look forward to seeing you all next week, and do let us know if you have any problems, but hope you enjoy the breakout rooms. Bye.